Hello. In this video presentation, I'll be introducing our paper on the root of trust identification problem as a part of IPSN 2021. And this paper is co-authored by Ivan de Oliveira Nunes, also known as me, Shihua Ding from Singapore Management University, and Jin Sudik from UCI. So before we get into the paper, let's start with some definitions. So what is a root of trust, right? The classic definition for root of trust is a computing entity with no ancestor entity capable of providing a trustable attestation for the state of it, which translates to whatever is the smallest piece of a system that you have to trust without verifying. So there are some examples for that. For instance, in the internet and in the public key infrastructure for the trust in the internet, the root certificate authority is a root of trust that signs certificates stating identities for other certificate authorities that in turn sign certificates for application services, right? So the root CA is the root of trust in this case. Within personal devices and computers, root of trust typically refers to a trusted hardware or a trusted execution environment. And also in the context of this presentation, we're going to be referring to those as roots of trusts and devices. So this trusted hardware and trusted execution environments, TEEs, they are present in many modern devices, and they are used by applications that trust them to be implemented correctly and securely to provide proofs for the integrity of the software running on these devices. So for example, they can be used to remotely measure software binaries, thus guaranteeing that the proper software is installed in a device, to measure execution and prove that the proper software, the expected software, is executed as a part of an operation, or even to measure the data integrity by proving that a particular output or piece of data was in fact produced by the proper execution of the expected software on a particular device, among other things such as the confidentiality of cryptographic secrets and sensitive data and other things like that. And examples of this TEs that we can commonly find today in modern devices are ARM Trust Zone, which is typically present in mobile devices, Intel SGX, and more recently, Google's OpenTitan. So in this paper, we focus on a particular problem related to roots of trust, or TEs, which is how to make sure that a particular TE task is being performed by the specific TE within a particular physical device. And this is made challenging because you have to consider that anything else other than the TE on that device may be compromised. And this is a reasonable assumption because this is actually the reason for being of TEs, right? We have TEs on devices and we use this technology to make sure that we don't have to trust the operating system and other layers of software on the device to be in a good state in order to be able to trust that actions are performed in the device without having to trust huge pieces of software like an operating system kernel and so on. So this work formulates and analyzes this problem systematically and proposes one candidate method for solving this problem of verifying whether a TE is executing a task within a particular physical device and outline requirements for future methods. But first of all, why should we care about this problem? So this problem is relevant whenever the task being executed depends on the physical location of a device. For example, if I'm asking, oh, can I trust the integrity of the data being reported by my particular sensor within an industrial plant or within my household, for example, fire sensor that I'm checking remotely to check if my household, if everything is okay, there's no fire and so on. And you can use TEs to solve this problem and to verify that the sense data that you're receiving right now remotely it's in fact produced by the correct execution of the expected software on your device, and therefore you can trust that this data was properly sensed by your device within your physical environment of interest. But what the adversary may try to do is, since it cannot corrupt the TE itself, this is an assumption, what it may try to do is to deploy its own sensor elsewhere in some other environment, and the sensor is also equipped with a TE of the same type, but it's not in your environment of interest. It's elsewhere, reporting, for example, that there's no fire or that the temperature is at the correct level, when in fact the actual sensed data in your device is not what you're getting when you retrieve this back. You're getting this sensed data sensed elsewhere. So whenever origin, meaning location, is important as a part of the integrity of your system, this problem is of interest. And it generalizes to several sense-based applications that relate to the physical world. So let's look into how one can try to solve this root of trust identification problem, the problem of figuring out whether or not a particular TE is running inside a particular specific physical device. So the first attempt, the first strategy that one may think of is, okay, that's easy. I'm gonna retrieve the public key corresponding to that TE, and I'm gonna play a typical authentication-based challenge response with the TE. And if the TE succeeds, I know that's the TE on my device. But this is basically just restating the problem itself. If I present you with one device and you want to know if a task is performed on that particular device, your challenge is in fact to find the public key of the TE in that device and then play the challenge response with that particular TE. So you can try to contact the device and ask, oh, what is the public key in your TE? And what might happen is that the device will reply with the correct public key and you're okay, or something else, malware on the device, or a network adversary may reply with the wrong public key, its own public key, or a different public key. And you think from that point on, you think you're interacting with the TE on your device, but you're interacting with something else, some other device. So basically, this problem arises from the fact that we don't know which public key TE corresponds, which public key corresponds to the TE within my particular device. So a second attempt is, well, let's use certificates. Certificates do exactly that. They bind public keys to identities. But the problem with certificates is that certificates bind public keys with digital identities. So for example, a certificate would look like this. Oh, the public key 129B5 and so on belongs to the root of trust number 16338 and so on. And another certificate for another public key, for another public key belong to another TE of the same type will look like, oh, the public key B7, B5, etc. belongs to root of trust number 2338. Well, okay, I know the root of trust identification number, but what is the identification number of the TE within my particular physical device? I still don't know. So basically, I just transferred the problem to figuring out the ID, but I still don't know. Right. So we're back to square one. Okay, so a third attempt may be, okay, if I can't find out whether or not this public key belongs to this TE within my device, I'll play the challenge response, still based on this public key that's claimed for this device, but I'll do it through a channel that it's a physical channel to my device. For example, a channel that no one else listens except for my device itself. And then if my device replies, I know that the response is coming from the TE within my device. So basically, if let's say you could use a wired channel, like a USB channel, or a visual communication channel, for example, you could display a QR code and use the camera on your device to capture the QR code, which is a challenge, which contains a challenge, and then the camera will pass this challenge to the TE will sign it and send back, and now you know that this public key in fact corresponds to the TE on your device because you're physically talking to that device. But in this case, we have to remember that the whole problem or the whole motivation for using TEs is that the device may be compromised, right? So what might happen if this device is infected is that malware on the device captures the challenge being sent to this particular device and forwards or relays this challenge to another device also equipped with a TE and under the control of the adversary elsewhere, not your particular physical device. And that TE signs the challenge. The malware relays it back to the verifier. And now you're convinced that this is the TE, the public key for your device's TE, when in fact, it is the public key of the adversary's device. So this is also not sufficient. Now, a fourth attempt would be, okay, since I can't, since this can be forwarded, what I'm going to do is that I'm going to prevent the forwarding by actually using the TE to verify that the challenge is being received through the expected interface. So now I know it's coming from the USB cable or it's coming from the camera. I'm not going to assign anything that doesn't come from that interface, which means the verifier must be sending it to me, right? Because the verifier has access to me. But what could happen still in this case is that the adversary could deploy its own fake verifier. And this fake verifier will play the challenge response through the proper interface. So the fake verifier is in the same physical environment as the dev ADV, plugged directly through a USB or displaying a QR code. And the fake verifier got the challenge from the compromised device, which is the original device that you want to figure out the public key for that device's TE, which received it from the real verifier. So still doesn't solve the problem. Basically, the adversary can use an accomplice device to convey the replayed challenge through the appropriate channel, whatever the accomplice TE device equipped with a TE is at a given time. So this doesn't solve the problem. And we can keep playing this game, and there are other attempts of solving this based on timing and distance bounding protocols, and our paper discusses this systematically, and we spent almost half of the paper looking into that. And the bottom line is, whenever a challenge is conveyed using a machine I/O interface, it can be replayed by another machine with the same I/O capabilities, unfortunately. So none of these prior attempts would ever work in the case where a device can be compromised. And there's no way for me to know if I'm actually talking to the specific public key. Or an alternate way to put in this problem is if I'm actually learning the public key corresponding to the TE on my device. So some takeaways is that we conclude after looking over multiple attempts of doing this is that either we need a direct exclusive channel from the communication interface to the TE, meaning that malware is unable to steal the challenge and forward it elsewhere, or we need machine unclonable challenges. So direct exclusive channels to TEs are hard to get because you have to implement the communication stack within your TE, which blows up the trusted code base inside your TE and kind of beats the point, because the point of a root of trust is to be small and something that you can trust. Now, if you put the whole TCP/IP stack in there, then it blows up. It starts to become, and driver code and so on, it starts to become like a kernel, right? And kind of beats the purpose. On the other hand, a machine unclonable challenge is something that machines cannot reproduce. So maybe even if you steal this challenge, whatever it is, an image, a random number, it's impossible for a machine to reproduce it and clone it and display it to another machine equipped with a TE to sign. So it's based on physical limitations of the adversary, right? And here is, based on these observations, here's one possible method that we propose to address this problem based on biometrics. So the main idea here is to put the user in the loop, right? And the key to this protocol is that we use the biometric as a challenge. A user's biometric can be any biometric. We do it with fingerprints. So basically, there's a verifier device and my device, and I want to learn the public key on my particular physical device. What I do is that I give my biometric to both devices. And the key idea here is that in order to reproduce my biometric elsewhere, the adversary has to clone me, or has to clone the user, or has to clone the user's biometric in real time, right? And then once both verifier and the device have the biometric, we play a challenge response based on the biometric itself. So the biometric is the challenge here. One additional nice feature of this is that biometric sensors are already present in many devices, and whenever they're present, due to the problem of keeping the privacy of the biometric, they are typically a part of the TE itself. They are hardwired to the TE. So basically, the secure channel between the biometric sensor and the TE already exists. And if you remember, I mentioned two basic conditions in order to be able to obtain a root of trust identification protocol. And you need one or the other. In this case, we kind of have both. We got lucky that biometric sensors are already a part of TEs. And USB channels or wireless communication could not be, because they're too complex. Right? So basically, we get both of these by putting the user in the loop and making sure that this biometric is something that an adversary cannot clone in real time, and just have that particular user elsewhere at the same time to do the replay of that. This is the basic idea of the protocol. There's, of course, several details that are omitted from this presentation, such as systematic formal problem formulation, how this cryptographic protocol using biometrics and based on fuzzy vaults and fuzzy extractors are used to produce the challenges from the biometrics. And then the implementation of a biometric-based root of trust identification protocol, and a hypervisor-based TE implementing all of this. If you're interested, please take a look at our paper for this details.